Okay, so hi everyone. We're super excited to have Elena here. I think Elena needs no introduction amongst this group. She's going to tell us about sieving and this new work, which I think is pronounced Jessica, which is a cool name. So yeah, take it away, Elena.
Thank you very much. Thank you, Noah, for inviting and for the introduction. So I'll be speaking about the work we've done together with Martin, with Leo, with Eamonn, with Gotti, and with Marc. And I guess half of the co-authors are now the participants. And please feel free to ask questions during the talk. I guess I could see the chat, or Noah will tell me about your question. So it will be about, so I was trying to structure my talk such that it's not too trivial, so I won't be really introducing the basics of sieving, and judging from the list of participants, the majority of you will know the basics, but rather what we've implemented in this Jessica sieving project, and which design choices were made. So, okay, this is a lattice talk, and I want to start with the lattice, and this will be like the simplest slide. So I need to introduce the problem. The problem we are solving is the shortest vector problem. So given a lattice, which is given by a basis, we want to find a short vector in this lattice. So typically we don't know how short the vector will be, but we have a rough estimate of when to stop our algorithms. And this rough estimate is usually given by the Minkowski bound, although I will mention later that the termination conditions for our algorithms may actually differ from just the length of the vectors. Like, as you can see from the Minkowski bound, it's the dimension that determines or rather the rank of the lattice that determines the length of the expected shortest vector, and also the determinant or the volume of the lattice. So to be more specific, the lattices we are usually working with, and these are the lattices that are, for instance, given in lattice challenges, these are the lattices for which we know the determinant. And for instance, like in the lattice, the basis for which I wrote on the slide is the lattice that has on the first column only one non-zero element, which is a big prime P, and the rest is just the identity matrix with the xi's, which are uniform random elements from 0 to p minus 1. And this lattice is, under some definition, looks random, and we know that the determinant of this lattice is P. And that's also why we know approximately how short vectors in these lattices are. But also we are not going to be super strict in finding the shortest vector. We'll also be fine if we are slightly longer than what we expect to be the shortest one, and by slightly longer, we could be fine with some constant approximation. Constant being 1 or 1 point something, 1 point something to the Minkowski estimate. What I also want to say in the preliminaries is the definition of the Gram-Schmidt vectors or the projected lattices, because this is what we are going to use in our algorithms. So since our lattice is given by a basis, so it has a short representation, what is also interesting is another representation of this lattice, meaning the Gram-Schmidt basis. And the Gram-Schmidt basis is a set of vectors, which I will denote by bi stars, and this bi star is just a projection of the ith basis vector on the subspace orthogonal to the space generated by the first I-1 basis vectors. So on the example below, you will have a lattice generated by B1, B2, and B1 and B2 star is the Gram-Schmidt basis. And the B2 star, as you can see, is the projection of B2 orthogonal to the space, orthogonal to the line generated by B1. And like if we do these projections for all the bases, we obtain what's called the Gram-Schmidt basis. And the reason why I'm talking about it is that because it's often convenient to represent lattice vectors in both bases, in the given basis B1, Bn, and in the Gram-Schmidt basis, just because very many operations on lattices are actually concerned with the Gram-Schmidt basis. So this is basically all we need from lattice theory to actually explain the algorithms. And the main algorithms we implement or that are realized in the in Jessica are the following algorithms. So we have the exact SVP, and the exact SVP is basically an algorithm, an implementation of SVP that compares the output against the Gaussian heuristic, or the Gaussian heuristic multiplied by a constant 1.1 or something around it. Another thing that is implemented is what's called Hermite SVP. This is, as I said, a good approximation to the shortest vector problem, and in particular, this is what is asked to solve by Darmstadt SVP challenges. You can also run BKZ or blockwise reduction, and as a bonus point, you can also run LWE solver that downloads an LWE challenge again from the Darmstadt challenges, creates an LWE lattice and solves and tries to find the unique short vector in this lattice. So I will not be talking. Yes,
so maybe I'm jumping ahead, but I'm just curious, should I think of these as just sort of like different interfaces to the same algorithm, or should I think of these as like completely different algorithms?
No, these are really the interfaces that we realize. So under the hood, these three algorithms will be actually calling either of the following four sieves. So you're right, this will be just different different interfaces indeed. So these are the interfaces that I'm describing. I'm not sure if this is the complete interfaces, but these are the most interesting ones. So as I said, all these algorithms, they internally call one of the SVP solvers. And the SVP solvers that we'll be interested in are sieving solvers. So in particular, the sieving algorithms that are implemented are the following four. This is the Gauss sieve, then Nguyen-Vidick sieve, or just NV sieve for the purpose of the talk. The code name BGJ1, that stands for Becker Gamma Joule with one level of bucketing, and that will be clear from what I will describe later, and the triple sieve. And the last two algorithms, namely BGJ1 and triple sieve, they are implemented in both single and multi-threaded fashion. And actually, from the implementation point of view, they do differ, like the single or multi-thread implementation, at least for the triple sieve. All right, so what I want to explain next is the last three implementations of the sieving routines, namely the Nguyen-Vidick sieve, the BGJ1 sieve, and the triple sieve. I will not be describing the Gauss sieve because I think this is, I mean, what is important as the last three. I mean, Gauss is also important, but I choose to explain the last three. So what does the Nguen-Vidick sieve do? The Nguen-Vidick sieve is just to make sure that everyone understands the sieve. This is about sampling lots of lattice vectors in a large list. And sometimes I will be calling the list a list, and sometimes I will be calling this a database. We called it as a database in the paper, and it means the same thing. So to be more specific about the sampling can be done variously. Like when we describe the algorithms, usually we say, oh, you just take the random linear combinations of the bases. You could be a little bit more specific about it, and in particular, what is done in the sampling routine is you could sample the last coordinates of your fresh vector with respect to the Gram-Schmidt basis and try to lift the obtained vector in the sublattice to the full lattice by using, for instance, Babai lift. Sorry. You could also think about doing something more clever than Babai by trying to sort of spend a bit more time on sampling, by trying to sample short vectors immediately. But currently we're not doing this trade-off, so the sampling that we have are efficient samplings. And this is the default sampler. Another default sampler, and another possible sampler would be to, if you have already a long list of vectors, you could just try to combine 3 would be a bad idea, 4, 5, 6 vectors from your list to create something shorter and call it a fresh vector. So once you sampled many vectors, you put them into the database and you start searching for pairs. And this is the main routine. When you start searching for pairs X and Y such that the sum of the difference is small. And how small is determined by a tunable parameter. And basically, whenever I say small in my talk, small means that this is up to the designer to decide when small is small. And the choices that are currently done are based on experiments, and like these should be smaller than for instance, the reduction is considered to be valid if the result is smaller than how should I put it? Then a certain threshold, and the certain threshold depends on the length of your lists on the length of the vectors in your list. Like for example, if it is shorter than the 10th last element in the list, in the sorted list, then it's a good reduction. If it's not, then it's not short. So once you find this small sum of difference, you put it into the list. And the difference between what is usually explained in the literature and what is implemented is that we do not replace X or Y, but we replace the longest vector in the list. This may introduce some dependencies, but we don't care about them. So by dependencies, I mean there could be collisions, because if you could continue, if you had fewer vectors, you would have found the same reduction again and try to reduce X plus Y with X plus Y, you will get 0. But it doesn't matter once you have enough vectors. All right, so, and you continue and you repeat that, you find the next short sum and you replace the current longest vector on the list. So here you replace like the next position and so on and so forth until you get enough short pairs. And if you continue this and if you start replacing enough vectors, you will soon see that you have a short enough vector in your list. So what I should also say here is that the termination conditions in the algorithms that we implement, they actually differ from just finding a vector that is shorter than a threshold, simply because what turns out to be more important in practical sieving is that it's not really the length of the only one short vectors, but rather the saturation of your space with many short vectors, which is more important. And if you start to actually run this algorithm, you will see that you would need that many vectors in your database. And this is actually quite accurate. So if you run it for large enough dimension, you will actually see that the asymptotics in terms of memory are quite good. quite correct, and the running time will be the square of the list size. Also here I should immediately in Nguen-Vidick sieve, I should explain how we actually search for close pairs. So basically all the time we search for pairs, all this algorithm is doing is it checks whether the sum or difference of the vectors is short. And the standard way to do this is to check the inner product. So if the inner product is large, then they are likely to give us a reduction. If not, then it's unlikely that they will give us a reduction. So basically the whole point of the sieving is to improve the inner product computations. And one way to do so, and this was already proposed in previous works, is to compute the scalar products approximately. And because of the way sieving works, most of the scalar products will be actually useless. And what is more important is to actually discard those inner products that are useless. And one clever way to do this is to introduce seam hashes. And seam hashes, they work as follows. We are going to store our vectors not only as coordinate vectors in terms of a basis, but also as they seam hashes with respect to a planes which we chose it randomly at the beginning. So for example, if we have, here is an example of how we store our vectors, or how we store seam hashes of the vectors. Like let's say you have 4 planes, V1, V2, V3, V4, and you associate like half of the one hyperplane of V1 with 1 and the other one with 0. So whatever is above V1 is 1, whatever is below V1 is 0. And the same for V2, V3, and V4. So for instance, vector y has coordinates 1, 1, 1, 1, just because it's on the one side of V1, on the one side of V2, one side of V3, and one side of V4. And similarly for x. So basically we're checking if this, from which side of a hyperplane x and y leave. So this is kind of a rough locality-sensitive hashing, except it is hashes to bits. So why this is efficient? Well, this is efficient because if vectors are close, it's likely that they will lie in the same half space. Well, if they are not close, there will be many half spaces when they where they differ. So, and in implementation, what is fast? What is fast is to take XOR and compute the Hamming weight. So, for example, for these two vectors, if we compute the XOR, because they collide on many ones, the XOR will be close to 0, and hence the Hamming weight of the result will be small. However, if you take the vectors that are not so close to each other, meaning that they will unlikely lead to the reduction, the XOR will be just a random binary vector whose Hamming weight is around ½ the number of bits half. So these guys we just discard by saying we're not going to compute the complete scalar product with the actual coordinates, but rather say no, they're useless. So this is kind of a rough sketch of vectors is implemented for all sieves. So where I do not only store vectors with respect to the basis, Gram-Schmidt basis, or just standard basis, but also the hashes. And whatever we do the check, we do this check first. Question.
So, you're saying that even when you do this like list size squared running time, so you check all possible pairs, but you still, like, before computing an inner product, just because that's expensive for you, you first do the top count thing.
Correct. That's precisely what
like from like a boring asymptotic perspective, this is like a constant factor improvement or something, but the actual
true. But yes. Yes, yes, exactly. So here we're actually striving for really, really fast thing, and we don't want to compute the product and the sum of floats, but we want to actually do the bits. And the reason being that XOR pop count is an instruction on many processors, and this is fast. That's all I want to say here.
That makes sense. Cool.
Yeah. So yeah, this is about Nguen-Vidick sieve. And this is about very basic hashing. What about not so basic hashing? And not so basic hashing is what's done in BGG1. And the BGG1 does the following thing. So basically it's in Nguen-Vidick sieve and buckets. What is a bucket? A bucket is defined by a center X, where X is chosen some randomly from our sampled database, from our list of vectors. And this vector X by itself defines a region. So here I just imaginary went from lattices to spheres, but this is for explanation purposes, it's fine. And also it approximates very well what's going on in practice. So what happens here is we take a random vector from a list and define a region. And by defining a region, I mean we just associate another vectors, all the other vectors from the list, with this chosen vector X by computing the inner product. And again, when I say computing the inner product, I mean first compute the rough inner product with sim hashes and then compute the exact one. So, and this leads us to the what's called the bucketing phase, or the first phase of the BGJ sieve is we define a bucket and we run through the list and associate with the center X all the Y's that have large enough inner product alpha. And alpha is again a parameter that we could choose. So if alpha is chosen, so what does it mean that that the inner product is large? It may mean that X and Y already give us a reduction. In which case we just, what do? We just reduce the Y and we put it again at the end of into the end of the list. But what happens if it doesn't reduce? We do not just discard Y, although it was kind of promising, but not promising enough to give a reduction. We put it into the bucket associated to X. And there could be several such Y's. In fact, there will be many such Y's in this bucket. And all those Y's, they're kind of conditioned on the fact being close to X. And conditioned on the fact being close to X, means that they could be also close to each other. And this is what is checked in the second phase, which is called the phase where we actually see the bucket. So we run through all the buckets we stored. Of course, we're not doing only for one bucket, but for many buckets. And we check, we now do sort of a naive double. There is a question. Maybe it's a minor point, but this definition doesn't necessarily partition the Y's. Some might end up in multiple buckets increasing the alpha. Does that matter? That's good. This is the good point. This is indeed doesn't partition. It could be that the Y ends up in multiple buckets, and it could be that it doesn't end up in any bucket. So if it turns out that it does not, it falls into many buckets, that means that indeed we chose alpha too big. So usually it's a good idea to choose output such that not many same vectors end up in various buckets, but it's all right. If that happens, it's not a big problem. So it is true that it doesn't partition; they could intersect. That's all right. So coming back to the bucket to sieving the bucket phase is inside this phase. We run through the buckets. We look at each bucket and we try to find pairs which are short between those vectors that are in the bucket. And now the difference between the Nguen-Vidick sieve is that now we do not do the naive two sieve on the original list, but we do the two sieve inside the bucket which is shorter, which is shorter than the original list. Now, asymptotically, that would we choose X randomly from the L, as I said, and asymptotically, if you do the that many centers, that is enough. Again, asymptotically to find all the pairs, your running time will increase for the naive square to this running time. And this kind of the running time you should be expecting from the current implementation. It's, I guess it's really hard to get this particular running time for the parameters and for the experiment that we ran, just because there were other improvements that I will be speaking of some of them later, that will actually affect, for the dimensions we run, this constant. But for large enough n, the BJJ1 implemented in Jessica should give this constant.
So, Elena,
there is a question, right?
Yeah. Oh, well, I think Leo was just explaining something to Huck. Yeah, I was wondering like where these numbers come from, like in particular, like I guess they depend on alpha. So this is like optimized for alpha or something.
Correct, correct. This is optimized for alpha such that it's with probability such that all but exponential small fraction of vectors will be lost using that. So basically, it's just how you choose alpha such that you cover, such that there is a high chance that you cover all the pairs that will be closed precisely, and this will give you this this constant.
This m, I assume, is like 4/3 to the n over 2, so it's like some beautiful geometric constant or something. These other things are just sort of like weird optimized constants, or do they have?
That's
like,
correct.
Okay.
No, so this will be just So this 142 is really you could compute it differently. One way to compute is the intersection of the wedges in high dimensions. And well, this is just the sum. This should be the sum of that.
Ah, I see. Okay.
Or maybe not. Or no. So this is just the number of centers times the bucket size squared. Yes. So, but this is basically this. So the runtime will be go through all buckets and do the sieve inside the buckets, which will be the bucket size squared.
I see. And Eamonn says alpha is chosen so the cost of populating a bucket is the same as searching within. So that makes sense. You're just sort of balancing these two.
Yeah, the alpha does the rebalancing. That's correct. Thank you, Eamonn.
Cool.
And let me finish the BJJ1 with comparing what is the current best one. And the current best one is what's called, again, BDGDL, sorry. It's Becker, Gamma, Ducas, and Larhoven. The difference between the BJJ1 and this strategy, which is best asymptotically, is that you do not choose the bucket center being random elements from the list, but rather they should come from a good spherical code. So X in the best asymptotical implementation is not a lattice vector, but it's unrelated to the lattice. It's a good spherical code, and the reason it's done is that because you want to make the bucketing phase, so they're associating a vector to the bucket can be done more efficient, in a more efficient way when X is actually from a structured spherical code. So asymptotically it works, but it also means that during this bucketing phase, you should decode random spherical codes. They're not of dimension n, they could be of smaller dimension, but this introduces large overheads. And as far as I know, Leo did some implementation of that, but it's not yet included. And well, it's just expensive to do the decoding. All right, so if there are no further questions about BJJ1 sieve, I could move to the triple sieve, and this is the sort of another. Oh no, sorry. I should say about before going to triple sieve, I should say a bit more about the way it's parallelized. So I won't be talking too much about the parallelization today. It's honestly, I forgot when I looked back to this code a couple of days ago. after not looking at it for quite some time, I actually forgot why we did some things like that. But okay, so the parallelization is done on the via distributing the buckets. So different threads work with different buckets, meaning that when they find something new, they actually, so the hard part of the parallelizing the sieve is that you actually have to update your list in a concurrent way. While reading is lock-free, meaning you do not, that there is no concurrency in reading the list, but writing the list actually may introduce some problems, because you actually, in order to write, you have to acquire a lock to do the writing, such that no other thread reads or uses the vector that you're going to overwrite. And for that reason, the insertions in all the parallelization versions, BGG1 or triple sieve, they are delayed and they're executed in chunks and batches. What is also not particularly trivial to do is sorting, and sorting is done differently between BGG1 and triple sieve. So in BGG1, the sorting is done by choosing a dedicated thread that does the sorting, and the other threads, if I remember correctly, they just, I mean, it's not a bad, it's not, nothing bad happens if you work with not necessarily fresh database. And well, the sorting is, although being complicated, but not so much of a trouble in the implementation for both BGG1 and for triple sieve. So this is what about parallelized BGG1. The parallelization happens between the buckets. So you distribute the bucket centers around the working threads. Triple sieve. Triple sieve is, if we look at it as a extension of Nguen-Vidick sieve, the main motivation for the triple sieve is to reduce the memory. Because the hope is that when you look not for pairs but for triples, you may need fewer vectors in your database to actually find reductions. You may need fewer vectors, but you may spend more time. And what it means if we were to run the Nguen-Vidick sieve for triples, that would basically mean going 3 times through your database in a search of X, Y, and Z that are whose sum difference is small, and there is a choice of signs for each X, Y, and Z. And again, once you find a reduction, you replace the longest vector in your database. And again, you stop when enough, not pairs, but triples are found, and once enough long vectors are replaced by shorter ones. And there are some theoretical, asymptotical results about triples that shows that indeed you can reduce memory at the expense of time. You could be even more paranoid about memory, and you can generalize 3 sieve to K sieve, but for implementation reasons, the increasing K for more than 3 seems to be impractical, while K equals 3 seems to be a good choice to do. And the way we do it is as follows. It's in particular good to choose K equals 3 in the view of the implementation of the BGG1 sieve, and here is why. So if you remember what I've just explained about the BGG1 sieve, is that we had 2 phases, the bucket phase and the sieve phase, and the triple sieve differs in the following way. So because we search for triples, we may allow for a bit more slack in the region alpha. And this is the first sort of change, is that because we are now looking for triples but not pairs, we could potentially go for larger regions. And again here, during the bucketing phase, you could hope that that some y's reduce with x, but here it's even less likely than in the BGG one, just because we sort of increased the region. But we increase this region because during the sieving phase, or the second phase, we do not only look for pairs within the buckets, but we also look for 3 reductions. And now the 3 reductions are done with the center and 2 other vectors inside the bucket. So the way that the triple sieve is done is that you again look into the bucket, and okay, if there is 2 reduction, you do the reduction, but you could also check if x and y prime give you something small. And of course, in my picture, it's unlikely that like this x, it's also impossible that x, y2 and y6 give you a reduction, but you should actually look at the signs. So it's more likely that y2, y6 and minus x, which is on the other side of the sphere, they might give a reduction. So there will be a choice of sign here that makes sense to ask when asked for something small. Now, in here is the so also for this triple sieve, it is important that x actually comes from the list, but not from the lattice, but not for instance from a spherical code. So if x was from the spherical code, then this last check wouldn't make any sense. And if we can tune the parameters, and by tuning the parameters, I mean tuning alpha and deciding what small means, we could actually interpolate between the 2 sieve and the 3 sieve. So what I mean by this here is that it turns out, and practical experiments it also turns out to be the case, is that if you actually restrict your memory and you can control the size of your database, of your list. So if your list is as large as is required for the 2 sieve, almost all the reductions come from these 2 reductions. So from the reductions between the 2 vectors. While if you start decreasing the list sizes, so in memory, the number of lists in your database, you can actually start seeing more of the 3 reductions. And if you go to the extreme memory regime where the triple sieve works, you immediately see that there will be almost no 2 reductions, but there will be more 3 reductions that appear, and this of course determines the running time of the algorithm. So
Elena, okay, I'm not very smart, but I would think that there would be like a pretty sharp threshold. Like once I have too few vectors to like fewer than whatever it is, 4/3 stand over 2 vectors or something, then I would basically never see pairs. But you're saying that's actually not true, that actually I'll see a decent number of pairs even if I go exponentially below 4/3 stand over 2.
So here what I've been talking here about the actual count of 3 reductions, but not the 2 reductions. But this is also, so I think we had statistics about 2 reductions, but so on the next slide I actually have a time memory trade-offs where you can actually see that. So this kind of should answer some sort of question about how sharp it is. And so what you see on the leftmost side is corresponds to the 2 sieve. This is so the number of lists which you should 1.3 to the n over 2. So this is really 4/3 to the n half.
I see.
And on this side, you would see what is needed for the 3 sieve to actually operate. This is on dimension 100. And so, yeah, so it's not really that sharp. It's
Right. I think I see
It's
where
like
my
that.
gone wrong. Yeah, like you're okay with like exponentially small fraction of the pairs being
Right.
working. Right. Okay. Sorry.
Okay, that's good. So yeah, as I said, we can the triple sieve. For the triple sieve, if you're on the triple sieve, you could actually find more reduction than the two sieve, so you could try to play with the list. And it turns out that in some cases it actually makes sense to decrease the list. And also if you target, if you're restricted to your memory, for instance, you'll see that for practical experiments you actually need quite a lot of RAM. You could consider running triple sieve, yeah, provided you don't have enough RAM. Okay, so parallelized triple sieve is again, parallelizing is done by dispatching the buckets. Again, reading is log-free. There is insertions are done again in batches, but there is still a big difference between triple sieve and PGJ1 sieve in the sense that the triple sieve actually, in the way it treats the database, the list, is more like a Gauss sieve than a Nguen-Vidick sieve. So it actually considers in the database the pair when there is the list, and the pair which is a queue, and the queue which contains vectors that were reduced and are about to be inserted into the list, and so on and so forth. I'm not going to go into the details. It's really not a very intuitive way to do this, but so the main point is that the triple sieve is also parallelized by doing different buckets, and the insertions should be treated with a bit more care, as well as sorting. So if there are questions regarding the internals of the SVP solvers, it's a good time to ask me these questions, because now I want to move to the part of the talk where I actually do not consider this. I'll actually go to what we're actually doing with this sieving algorithm, with this implementations of the sieves. I see no questions. I will continue.
Well, I have one more dumb question. So if I understand correctly, the reason that k equals 3 is so convenient is because for both k equals 2 and k equals 3, you only have to iterate through pairs of vectors inside the bucket.
Correct. So this is just the, yeah. So it's just the convenient way to do sieving inside the bucket, where the bucket is actually labeled by the lattice vector.
I see. And somehow like that, the general function is just like either 2, like the maximum of 2 or k minus 1 or something. So like you never get any benefit from any other k.
Does seem like that, yeah.
I see. Weird. Cool.
Okay. So what is done apart from just SVP solvers? So the way you could treat SVP solvers is actually quite interesting what you can do with that. And the framework itself, so the ideas that are implemented in Jessica, they actually include many previous, and they introduce some new improvements for sieving, practical improvements for sieving. And I want to mention 3 of them, and I will explain on the next slide what each and every one of them mean. So the first one is called progressive sieving, that was introduced independently by Leo, by Manario, and by Thijs 2 years ago. And that means that progressive sieving, so you don't have to start with to sieve in the full dimension. What you could do is you could maybe try to sieve on the lattice on the sublattice of a smaller dimension, and somehow use this this database of short vectors, but they live on the sublattice, to actually improve the sieve of the proof in sieve in the high dimensional lattice. The dimension for free trick is utility that tells that, well, okay, maybe I should not actually sieve in my full lattice again, but maybe once I sieve in a projected sublattice, and then all the sectors that live in the projected sublattice, they're short enough, maybe they by lifts will by lifts to the full lattice will give me something short, because if the hope that something short in the full lattice has a projection that is also short. But you could also hope in the opposite direction that is true. And what's also interesting, what's implemented in the framework Jessica is the PKZ algorithm, so blockwise reduction, that does not use SVP solver as a black box. So because sieving outputs not only one short vector, but possibly many short vectors, it does make sense to actually recycle the short vectors in between the PKZ, the PKZ routes, the PKZ routines of calling the SVP. And again, I will return to this in the next slide. So behind all of these improvements, there are sort of basic principles of how to use sieve in the how to use the output of sieve or the internals of sieve in the optimal way, or what we think is optimal. And the first one is to actually notice that sieve outputs many short vectors, but not only one. And what is also important to understand is that we do not really try to find one short vector, but we want to find many short vectors. And within the run, we try to improve the quality of the basis rather than just outputting one short vector. And the quality is measured, as it's not surprisingly, in the length of the Gram-Schmidt vectors of your basis. So in order to get...
Sorry, Elena, here you're saying that like when you run your sieving, you don't just, and you're inside BKZ, you don't just update the first vector in a block of size K, you update like all K vectors on what you sieve?
So what I'm saying, what I will say about BKZ is the following. So once you do sieve in the projected sublattice, let's say projected sublattice from I to J, and then once what the BKZ does, then it moves from Y to J to I plus 1, J plus 1. Mm-hmm. And what makes sense is to lift the I plus J context into I plus 1, J plus 1 concept and hope it's still short, which is true. It's kind of short. Yes. And then you don't start from scratch, but you rather run the sieve on this new vectors. So that's what I want to say.
And this is again, like, I guess this only really saves you like maybe a factor of n or something like this, but like in practice, that's a big deal.
It's really hard to say how large it saves in terms of the quantity. Like I wouldn't say it's really n, but yes, in practice it seems to be helping. It seems to work well, mm-hmm. And this is also a reasonable thing to do, I think.
Cool.
Right. So let me tell you a bit more in detail about the first three. About the progressive sieving, the dimensions for free, and the BKZ, and a bit more in a bit more detail. So for that, I just need one more, just to make sure you understand my notations. My notations of the projected lattice will be the following. I'm saying that I'm returning back to my GSO picture, is that I will be denoting by Lij the orthogonal projection of the lattice generated by the first J vector, orthogonally to the subspace orthogonal to the first time minus 1. So for example, this will be L2, and Lij should be thought of as it's a lattice of rank J minus I plus 1. And with this notation, which is a standard notation from the lattices, we could define SVP sieve in a sort of non-black box manner. And sort of the main feature of the of Jessica, of the kernel of the algorithms we implemented, is we kind of play in between this, in between the several set of instructions that move from one projected sublattice to another projected sublattice. So for example, what you could do is you could lift short vectors from one sublattice, projected sublattice ij, to another sublattice I plus 1j for where I prime is less than I. So meaning you just, so that means you just project one vector up. So you just, so previously you were projecting to L orthogonally from 1 to I minus 1, and here you project orthogonal to 1 to I minus 2. So you kind of lift up using Babai lift, for instance. What is also done during the sieve routine is that we try to update the current basis with particularly good lifts. So if you do the sieve and you kind of start what's called on the fly lift, you lift it up to the whole, to the full lattice and see if it's good or not. And if it is good, you could update your current basis. And all of this is all the operations on the lattices could be described by a small set of instructions. So moving from one projected sublattice to another projected sublattice could be done by either lifting, which is just a Babai lift, meaning that you just lift up using Babai. You could run inclusion, meaning that you move from ij to ij plus 1, so you just add one more vector to your current projected basis. And projection is the opposite. You just project out one vector, so you increase the dimension of your current lattice by 1. And just let me explain with these instructions, with these more formal instructions, what could be done within the framework. Just repeat the instructions so you could see what they mean. The progressive sieving meaning that you just you do not start on the full dimensional lattice, but you start with sublattices, is nothing but the iterative sieve in the projected sublattices LIN for decreasing i's. So first you start with something that is it's just one dimensional, so it's orthogonal to everything but 1. Then you just add one more dimension, and you just add another third dimension, and so on and so forth. Each time you start not from scratch, but each time you already sieve in the lattice for which you sieved on the sublattice. And this kind of could, this thing does help. So it's kind of a pre-processing. You could think about it as a pre-processing step for the next sieve. The second improvement that's also relevant for practical thing is dimensions for free, where you do not sieve until the very end. You stop this progressive sieving, maybe not when I is equal to 1, because when I is equal to 1, you're in a full lattice, but maybe when I is somewhat close to 1, but not so much. So in that case, you could, like what Leo did in his Eurocrypt 2018 paper, is he shows that if you stop in the n over log n dimensions before you had, so you would need n over log n dimension more to get to the full lattice, you're already good enough to sort of lift up with Babai lift your short vectors in this lattice to get a good chances, to have good chances to obtain something short in the full lattice. So this is kind of this n over log n factor. It could remind of pruning factor for the enumeration algorithms, but like in the nature it's different. But in terms of quality that it brings, it's similar. And you can also see that in practice it also works. So we do not for the challenges that were solved, it was not necessary to run the sieve on the full lattice. And the another instructions that were sort of realized and implemented in G6K is what's called pump. Pump is just a set of instructions that runs progressive sieve from a small lattice, or from a small dimensional lattice of rank 1 to the lattice of rank n minus I plus 1. And doing this progressive sieves, it updates the basis by inserting the short vectors into the basis. And also using this pump, you could what's called workout, is that it executes this progressive sieve for decreasing i's. So you just run the progressive sieve not for I, but for I minus 1, and then I minus 2, and so on and so forth. So you do this pre-processing with each dimension increase. And so all of that, you could also, using all of that, you could run BKZ. So BKZ is the blockwise reduction. And just let me tell you a couple of more words about how BKZ is done in G6K. So the simplified version of the plain BKZ is here. You have you call SVP oracle on the beta dimensional lattice, a projected lattice of dimension beta. And once you find something short in this calls to SVP, you update your basis by inserting what you found, and you remove some linear dependencies. So if you're giving an n-dimensional basis, you run SVP on the beta dimension, then you move these from 1 to beta to 2 to beta plus 1, and so on and so forth. What you could do if you run SVP if you're not oblivious to what SVP does, in particular if your SVP is a sieving algorithm, you might as well want to reuse not only one vector, which is short, but also many vectors that are short. So in particular, you could rewrite the BKZ algorithm by just calling the sieve on this kind of lattices, and by noting that each time you do that, you have an inclusion of your sublattices. So once you're good here, once you increase your dimension, so this is like the progressive sieve, you're already good. You hope to be not so bad in this lattice. And also, once you sort of move back, once you move your context from k plus beta to k plus 1, k plus beta plus 1, the point of this is that, as I explained previously, you could just, so what it means, you just, you lift up in one dimension and you project back into the other dimension. So basically you're 2 dimensions away in your context. And if you were short, and if the beta is long enough, large enough, so that gives you a hope that this lifting and insertion leaves you with something short. So it doesn't spoil the work you've done on the previous run. So that's how you could, for instance, use BKZ. Receiving, this is a simplified thing. You could check the paper for more detailed version of that, but the idea is this. So if there are questions for the theory part, I would rather take them now, because I have couple more slides about experimental results. And the experimental results that were reported, and we've been doing them on, we chose Darmstadt challenges just for comparison reasons. And so this is the results. By the time we published the paper, and this was 1 year ago, that was previous year. the Hall of Fame and Darmstadt Challenge site looked like that approximately. The way we managed to solve, SCP in dimension 155 within 14 days and lots of CPUs. Well, I don't remember how. I don't exactly remember how many threads we've been using, but it could be either, I think it was around 80. And we used a lot of memory. So it was a good machine. Thanks to Martin, we've been using his machines to run the experiments. So as you can see, we did not have to run SVP in dimension 155. Thanks to the dimensions for free trick, the actual dimensions we ran the sieve on was 127. So this is approximate level of savings you could get. And these experiments were done with BGJ1. I should also mention that it's not the current best record. I checked the whole frame today, lunchtime. So the current record is still due to Leo, Marc, and Vessel, and they managed to solve dimension 157. And if I remember correctly, this was using GPUs. So all the things I was talking to you was not on GPUs, it was on CPUs. And I do believe that on GPUs, if you're smart enough, you could probably do more things with GPUs. But these were not GPUs, and also this implementation was not distributed. So it was one machine. It was one but good machine. And yeah, we did require quite some RAM to run it. So this, by the way, improves the previous best record for enumeration. That was, if I remember correctly, it was about 150 dimension, 152.
Elena, this is done with this not exactly triple sieve, but like this.
It's BGJ1. This is BGJ1.
Oh, okay. So it's just pairs, not triples.
There's just pairs, yeah, correct.
I see. Oh, and you still managed to get the memory below, I guess like 256 gigabytes is probably a pretty big constraint.
Yeah. So I think that the biggest experiment was 155. We've been running on 512 gigabytes. But yeah. And also I should say it's like, so although I'm kind of showing here the experiments for large dimensions, the sieving in this implementation also improves our enumeration implementations of FPLL. Not on, I mean, the improvement was on the dimensions 80 or 90, I think 80. So kind of this golden crossover point is below 100. All right, so I'll leave my last slide with the link to the library and with the link to the paper. It's open source. So the core is implemented in C++, and the friendly interface, as Martin likes to say, the friendly interface is implemented with Python. So you can download it and use it. So you would need FPLL, or you would need FPLL for that. And okay, I guess I'm good with time for questions. I'd like to thank you for your attention. I take questions, and at the end there are references which you can find also online.
Okay, great. So that was wonderful. Let's thank Elena. If you can, quickly unmute yourselves and applaud, that would be great. So
thank you.
I feel like we're getting way better at that. So if anyone has questions, I guess now's a good time. Oh, you also have chat applause.
Yeah, do you see the chat I'm opening? I'm not sure if
No, there's just applause right now, but let's see if anyone has questions.
okay.
I think
I'm waiting.
I have many, but I probably exhausted
Okay.
the schedule of questions.
No, you go ahead.
So not just Elena. So
Yes.
this G6K thing is on open source, GitHub, and so on. So is there also enough, like documentation and examples for people to easily figure out how to use it? Or I mean, just being open source is not. I mean, it can be a big effort for anybody else to use something, unless you want to do software development.
So I think it's probably a bit less documented in terms of the manuals as FPLL at the moment, but definitely what was done during the Simon's workshop is Martin was doing labs. And I think it has a pretty good lab sheet how to install and how to use Jessica. So I guess, I'm not sure if it's online or not, but I'm sure that if you ask Martin, he will put it online. But currently it's, so the instructions how to install is basically as good as the instructions for FPLL. And if as soon as you can...
Installing is just the first step, and I see there are installation instructions on the GitHub page. But I mean, once you install it, then what do you do with it? Let's say I already have it installed. So let's say this.
Yeah.
So it's how do people go from there to actually using it? Is something that I didn't try. I'm not saying that it's not there. I'm just asking if it's something that.
So I guess it depends on which level you want to actually play with it. If you just want to play with the parameters that we chose, this is pretty simple and the examples are there. So you could just instantiate the siever as we can just instantiate the siever and run it and redo all the experiments that we've been doing. And for all the experiments that we've been doing, there is actual line of command that you should input into your machine and you should recreate the same experiments as we had. This is one thing, and this should be simple. This should be simple enough, provided that the information is there. Now, the different thing that if you want to actually, I just moved to that. Haha, I didn't want to do this, but I managed. Yeah, so these, okay, now since I moved it, I can also show you. So reproducing all the experiments that we've done is explained in the on the GitHub page. So this should be as simple as that.
What you're showing right now. We still see your slides because you shared the window, not the screen.
Right. That's interesting how to redo
that. Maybe if you stop sharing for a second and then reshare.
Yeah. You share. Very good. And I can share the desktop now.
Yes, good.
Yes. So yeah, so basically, so how to reproduce the experiments from the paper, this you can do by just copying, pasting this in the command line. What to do if you want to do if you want to use Jessica from Python, you can also do that, and by specifying the algorithms. Like I'll explain here, for instance, and this is nothing else but just standard.
But these are examples. So these are exactly examples of what you do to run something on your own.
Correct.
Okay.
Correct.
Okay. Good. And it is on the GitHub, on the FPLL GS. Okay. I see.
G6K GitHub. Okay, but what I want to say, if you actually want to change the alphas and on the parameters of the sieve, like the sensitivity of the shortness, the way you handle the size of your database. So if you want to change this part, then you actually have to go into the code. Now so you have to recompile that because some things are actually compile time constants.
Okay, thanks.
Welcome.
So any more questions? Okay, if not, let's attempt to do this clapping thing again. So
thank you.
1, 2, 3. Not as good that time, but that's okay. Let me stop the recording.
Right.